diagram. So in this case, then I'm going to draw a rough idea of what we did.
Okay.
Now I can do this in any situation, and I'm just going to draw an arrow, an arbitrarily long arrow. I don't have to make it any specific value. But what I'm going to do then is assign it a length of 5.0 meters. I drew my arrow up just to mean north, but it could be anything. Now, keep in mind, this doesn't have to be a 5.0 meter long arrow. I could make it in meters per second or newtons or whatever it is I'm looking at. Vectors work the same way. The key thing then is just to draw a rough idea what it looks like. Now, if I do that, then afterwards, I go 3.5 meters east. The key thing with vectors, here I want to add the vectors. And vectors, which are these little arrows, they always need to be added head to tail.
Shoot.
So if this right here is, it depends what you call this thing right here, but in this end right here, if I start here, I finish here. Right? I mean, I go from here to here, then from there I have to go east. Okay, so in that case then, I would draw an arbitrarily long arrow. Now, I probably want to make it shorter than this one, just to have a rough idea what it looks like. I'm going to label it 3.5 meters. All right, well, what's the difference then? Haven't I just gone 8 meters? Well, displacement, what that means is that's the distance from start to finish. In other words, what I'm really asking here is, how far am I from my starting point? Right, I started here, I finished here, so how far have I gone? And not how far have I traveled, but how far am I from my start point? I'm going to draw this maybe in a different color here, but my place where I'm actually sitting here, I could draw this vector here, and that's going to represent my displacement. Maybe the blue isn't showing up in enough contrast, so I'm going to keep going with white. But in this case right here, I want this vector. In other words, I want the length of this thing. Now, if you look carefully at this diagram, I've got this in, well, it's a nice triangle. It's a right angle triangle. This one here is 90 degrees. And so then I can use a nice trick. And I don't know if you remember this, but it's Pythagoras' theorem. So in this case right here, I can say, well, this is the hypotenuse, right? It's the longest part of the triangle. I like to think of it as opposite to the 90 degrees. In other words, if you're that angle 90 degrees, this is what you'd be looking out at. Imagine if you're there looking this way. You'd be looking out at the hypotenuse. So in this case right here, Pythagorean theorem helps us because we can say then that s squared equals, I don't know if you remember it, but it goes c squared equals a squared plus b squared. So in that case, s squared equals 5 squared plus 3.5 squared. Okay, that's what I need to look at. Therefore, s is going to be then the square root of 5 squared plus 3.5 squared. Technically, it should be plus or minus the square root. That's the mathematical solution. But we also have to look at what actually makes sense. And in this case, it only makes sense to have a positive square root. So I'm going to say that like this. So 5 squared plus 3.5 squared. Now I'm just going to reach out and get my calculator because it helps to have one of these babies. Either the TI-83 or the TI-84. I've got the old school TI-83, but it works just fine. It calculates numbers just fine. So 5 squared, well, that's 25. And I want to add to that 3.5 squared. And then I want to take the square root of the answer. And I get s is equal to 6.1 stuff, but I have to look at how many digits I'm allowed to use. So in this case right here, 6.1 meters. But I'm not done yet.
Holy fuck.
Okay? Because that's just the magnitude, but I need the direction. So I need to know what angle, where am I facing in order to get from start to the finish here. And that angle is going to be given by this angle theta here. Whoops, I should probably draw a proper theta. If you're Greek, this is just a regular letter T for you, but this is angle theta here. So I want to know that angle. And if you remember your right angle trigonometry, you should be able to figure it out. So we would say then that the tangent of theta is going to be 3.5 divided by 5. Now, if you don't remember how to do it, at least in English, we have a trick, right? Because not everybody watching this is necessarily English as a first language. But I know that in Canada, we learned a trick called SOHCAHTOA. which tells you about sine and cosine and tangent, and how they're related to the opposite and adjacent and hypotenuse. So in this case right here, tangent is the one that goes opposite over adjacent. So at least in English we have a little trick, so, ka, toa. What it really means is sine equals opposite over hypotenuse.
In the front of you for HP.
Cosine is equal to adjacent over hypotenuse. And tangent equals opposite over adjacent. That's what the letters stand for. If someone says SOHCAHTOA to you and you've never heard of it, that's what we mean. It doesn't matter though how you do it, as long as you can get to this answer that tangent of theta is 3.5 over 5. And therefore then theta is going to be, well, the inverse tangent of that answer. So 3.5 over 5. So in that case then I get out my trusty old calculator and I'm going to actually say 3.5, divide that by 5, I press enter, and then I'm going to say inverse tan of the answer. And I get an answer of about 35 degrees. So I'm going to say theta is equal to approximately 35 degrees. Now, it's important though when you're working with angles to keep in mind what mode you're in. So I can press mode and I can make sure that I'm in degree mode. You probably can't see that from there, but there's something called degree mode. It's really important to make sure you're in the right mode. Because in a math class, you're often switching from degree mode to radian mode. And in fact, there is one example where we need to use radian mode in physics. That's in the physics higher level core topic or the standard level option with waves. So for standard level students, it's going to be called side and wave phenomena. For that one, you actually have something with Rayleigh criteria and working with those angles where we need to actually be in radians instead of degrees. But most of the time, we work in degrees. So I'm ready to put this all together then. So therefore, my displacement, right, with this little s with the arrow then, I'm going to say it's 6.1 meters. And then I'm going to give the bearing. So in this case right here, bearings start off north and then they always go clockwise. So in this case, it's really easy. Start off north and go just 35 degrees to the right. So we often just say 0, 3, 5 degrees. That would be my answer to this. My displacement is 6.1 meters away from my start point, and it's at a bearing of 35 degrees from where I started. Now you could also actually say for this direction, you could actually say north 35 degrees east. There's a number of ways of doing that. I know that bearings are really important, especially if you're doing flying, which I used to do some of, not with my hands obviously, but in airplanes. And their bearings are really important to know which direction you're actually facing. So in this case, I just prefer bearings just because I used to use them a lot. But in any case, that's actually an example of vector versus scalar. Okay, we can actually see that the distance is totally different from displacement. In fact, this is a really cool situation. What if you walked around in a big giant square? Well, your distance traveled will be something, but your displacement would actually be 0. It's possible for displacement to be 0 even though you went traveling around. Right? What if I start here, I go for a walk around this room and I come back? Displacement means how far am I from my start point. And if I've gone around and finished where I started, my displacement could actually be 0. In this case, notice though, my displacement is very different from my distance traveled.
Nice. Oh, all long. Why, orange? It's not fun, I need win. Torang. Yo, cheat.
Accuracy, precision, and error come up very often on IB exams. And not only for that reason, but it's certainly a motivating factor, is I think it's really interesting to do in physics, is to think about these concepts here. So first of all, let's start off with accuracy. What does that actually mean? Okay, so if something is accurate, it's something that has a small systematic error. Okay? A small systematic error. And this will mean something that's close to the real value, so to speak. So I'll be talking about these in a second here with some examples because I think it'll help. So something that's close to the real value. My U looked like an N here. There we go. Now I'm going to use a different example. I'm going to leave a bit of space here, so just bear with me. I'm going to leave a bit of space, and I'm going to say what precision is. So precision, I'm going to show you by comparing the two. So precision is something with a small random error. Okay, so something that is precise has a small random error, and there you could say close to each other, the values. Now this may not make much sense, so what I'm going to do, oops, just make this look like an E. I'm going to give you an example. So let's say that you are an archer and you're shooting at targets. It's a common example to use, but I think it's actually relevant here. So let's just say you're shooting at targets. So here's the center, and here's the whole target. I'll give you an example here. Here's the center. Here's the whole target. So the goal, of course, is, let's say you're shooting arrows. You want to get them all in the center. Now, if you're, now you could be accurate, you could be precise, you could be both, you could be just one and not the other. So I'm going to give you an example of something that's accurate, but not necessarily precise. So accuracy would mean, maybe close to the real value. So maybe you're a little bit like this right here. So these would be, where you shot. Now they're centered around the correct value. So in that case, around the center point of the target. But in this case, it could be something else. This could be a lab experiment where you're trying to find what the value or the acceleration due to gravity is. Now, if you already know what the answer should be, then you can really tell if something is accurate. Sometimes you don't know what it should be, so sometimes it's a little bit harder to tell if you have a systematic error or not. Right? Because you don't want to do an experiment only looking to match an answer. You want to do an experiment to see what you get. But in this case right here, if you know what you're supposed to get, in this case you're trying to get to the center, you're near the center, so you could say you're accurate. Now if you're precise, this means a small random error, so that means maybe the values are close to each other. So maybe you're off, so maybe a whole bunch of your arrows all hit around this spot right here. Now, I would say that these ones right here, then they had small random error. In other words, they're all pretty much going the same place, right? They're all close to each other, but they're not necessarily near the center. So this is something that's precise but not accurate. This is something that's accurate and not precise. And clearly you can have something where it's accurate and precise. I know that when I was in the military, we would go to the shooting range during the basic training. Maybe it sounds a bit violent, but trust me, I didn't want to shoot at anyone. But in this case, we would actually go to the shooting range and try to shoot at targets. And when we were shooting at targets, if you did something like this, for example, it probably meant that you actually have small random error right here because you're in fact, you'd be shooting really well, we would say. But the problem was maybe your sight or your telescope or whatever it is you were using to help you aim is maybe not calibrated right. In other words, all your values are always going a little bit right and a little bit up from where they should be. So what you could do, of course, is you could adjust your little sights on the little iron sights on the M16, or if it's in Canada on the C7. But what you could do then is you could adjust the settings until that would go here. So that would be an example of something that where there was systematic error. Systematic error means even if you repeat it a bunch more times, you're still going to be here. So that's an example of systematic error. If there is some, repeating it won't really help. Your values are sort of off by always the same amount. But if you know that it's systematic error, you could always just take your answers and then just sort of subtract or change all your answers in order to match what they should be. Sometimes it's possible in an experiment to do that. Right? Here was an example of someone who's maybe not very good at shooting, so maybe they weren't very good at controlling their breathing, for example. Sometimes it would happen where if you're not breathing well, you'd actually be shooting and you'd have all the targets would all be hit up and down because you're not breathing right. Or maybe you get someone who really pulls the trigger hard, and if that happened, oftentimes their target would be hit left to right. So sometimes this is just an example of someone then who's maybe having a lot of a random error. So in this case then, small systematic error means close to the real value. Small random error means close to each other. And sometimes they can be one or the other or both. Now if we talk about error,
can I have the AK, please?
I actually want to show you an example of maybe something from a graph. So maybe you're actually doing an experiment, and maybe you're actually trying to measure, for example, this could be an example with springs. So maybe you're actually trying to measure this right here, or at least test this relation, that the force between a spring is equal to some spring constant times its displacement. Okay, so you could be doing this experiment with a bunch of springs, or it could be anything else, but usually it's done with springs. You could hang a spring and then hang a weight to it, and then you'd know the force. You could calculate that, and from there you could look at how far it's displaced from its equilibrium value. And if you did a graph of this, you would expect to get a straight line. Okay, so if we graphed x, which would be in meters, and if we graphed f up here on the y-axis, then maybe you get a bunch of values. So I'm going to show you an example then of what you could have. Let's actually look at an example of something with systematic error. So in this case then, let's say all my data points are like this. Let's say so they work really well. By the way, you'd have to draw little error bars everywhere. So let's just say I've drawn my error bars correctly, because that's what you do in a lab. Right, that's a bit beyond what we need to worry about here, but let's just say this is what I got. Each of these centers is where my point is, where I measured it, but I'm not entirely sure where it could be, so I allow it to sort of be maybe as high as this, maybe as low as this. The units here don't really, not the units, the values don't really matter so much. I'm just trying to show that if I drew a line of best fit, with these, I could try to sort of use my eyeball here and try to say, well, it'd be something like that. I'm not very good at drawing straight lines, but this seems to have worked out okay. Now, if you look at this, you might think, well, what kind of error do I have? Well, here I have a systematic error. And the reason I know that is because this is something that's directly proportional. In other words, this is like y equals mx, if you remember your equations of graphs, of lines, straight lines, that is. So if this is y equals mx, there's no plus b here. There's no y-intercept. That means I expect this relation to have a y-intercept of 0. In other words, it should cross this y-axis here, because this keeps going.
Oh,
right?
so you stole people.
I can have these axes extend. I would expect it to pass through this point, but it doesn't. And so that means, and I could say that I have a systematic error. That means something's wrong in my experiment. So maybe I'm measuring everything wrong, but at least I'm measuring it equally wrong. Right, so if I really wanted to be accurate with this, if I really wanted to, be accurate, I would try to make my systematic error smaller. And I could do that by recalibrating it. Do you notice if I kept repeating this experiment, it wouldn't really change much, right? My systematic error wouldn't change. Now I'm going to give you an example of something that maybe so that's systematic error. What if I did the same sort of thing, but this time, while I was graphing these guys here, what if my lines are like this? Then I could, of course, with error bars. I'm just getting bored of drawing these error bars, but let's just assume that I've got my little error bars drawn. There we go. Now let's say my points are located a lot like this. They're really kind of messy. They're all over the place. If I try to draw a straight line, I could imagine that my straight line sort of passes through here. So then I could say, well, that means then I probably don't have much systematic error, but I have plenty of random error. And that means that, while I was measuring it, whoops, it's a little bit too high or a little bit too low. And in fact, a line of best fit should pass through the error bars. So in this case right here, this doesn't really look very nice. This really wouldn't be a very good example of something that actually works. However, what if I had the same kind of experiment, except let's say I had big error bars here. So I know that I had this point, but do you notice that these error bars now sort of touch that line? What if I had a point that was here with big error bars here? What if I had another point here with big error bars, and this thing ended up falling within all my error bars? Then I could say, okay, it might be sort of a crappy experiment, but it's not that bad, because at least most of my points touch the line of best fit. At least the error bars do. But if I have one point sitting all the way over here on its own, I could say, aha, that right there, that is a random error. And I could actually, if I want, I could actually omit this. I could actually forget about it. And I could say, I'm going to ignore this point because it doesn't, well, it's a random error. That means I must have made some sort of mistake. If I repeated this experiment, it would get better, and this error probably wouldn't be there.
No name. Go be. No name. My AK. AK.
Uniformly accelerated motion is another really important part of topic 2, which is mechanics. Very first thing I want to show you actually is the opposite of uniformly accelerated motion, which is not accelerating motion. Okay, so in that case right there, just to be a little bit clear here, I just want to write down sort of a distinction right here. So if it is not accelerating, then it's actually really easy. Okay, so if it's not accelerating, then you use just the regular equations of motion that you've probably learned a long time ago, which is that the speed is equal to the distance divided by the time. In this case right here, we could say v equals s over t. Right? Remember, s means distance. Now this could also be the vector version. It could be the velocity is the displacement over time, or it could be just the speed is the distance over time. Either way, this is really, really easy. That's all you have to do if it's not accelerating. So that's really easy. However, if it is accelerating, then the speed changes every second. So this could be like you in your car, for example, and then if you step on the gas, well, what happens? Well, that means then that you change your speed, right? So you go actually a little bit faster. So in that sense, that's when you have acceleration. Another example of acceleration could actually be, let's say, you just drop off a cliff or something like that. I mean, if you do that, you actually accelerate because your speed increases, and then it increases some more, and it increases some more. So that's what we mean by acceleration. Okay, so if we're actually looking for accelerated motion, okay, so what we do is we say it's uniformly accelerated because we're assuming that the acceleration is the same. We're assuming a constant acceleration. Okay, so we're assuming that we have some sort of acceleration value that's actually constant. What I'm going to do is just put this just off to the side a little bit, just because that's just part of it. If it's not accelerating, then you do that stuff. But if it is accelerating, then we have some equations of motion that we can actually use. So in this sense right here, we have what I like to call the 4 equations of motion. Okay, so if we look at these 4 equations of motion, not all of them are on your equation sheet or on your data booklet. If you haven't seen it before, this is the data booklet. Well, it looks just like a white piece right now, but so you can see I'm actually not that pale. See, there's a slight difference in my skin tone color compared to this white piece of paper. But this is your data booklet, and I'll be showing you this in more detail because obviously it's hard for you to read it right now. But if you take a look at it, what's really important is that you get some equations here, especially to help you out with topic 2. But in my opinion, at least, there's some equations there that are not in your data booklet that are actually really important to use. There's very few of them, however. So what I'm going to do is, as we go along, I'm going to make sure to highlight the ones that I think are worth memorizing. There's not very many, but the very first one I'm going to give you is actually one of them. So the first of the equations of motion that's not given in your data booklet is this one right here. V equals U plus AT. I consider that sort of equation 1. I'll explain what each of these means in a second here. But so that one right there is not in your equation sheet or data booklet. I should call it the right thing. However, this one right here is. Okay, so we have S equals U plus V divided by 2, all that times T. Sometimes we put a little bracket here. And then we have a third one, and that one is this one here, S equals UT plus 1/2 AT squared. And then we have a final one, which is V squared equals U squared plus 2AS. Now these three right here are on your equation sheet or on your data booklet. Okay, these three right here. This one is just worth remembering because, well, first of all, there's not so much to it. Just V equals U plus AT. I think, though, it would help to actually write down what each of these letters means, because without that, it doesn't really tell us much. So in the case of these ones right here, you might recognize S, and you might recognize T and V, but then we have a U going on, and you might not be sure. So just to be absolutely sure that we're talking about the same things, I'm going to tell you what everything means. So U is the initial speed or velocity. In this case, let me just say initial velocity, but it could be a speed as well. So U is initial velocity, and that will be measured in meters per second. Now, the way I remember what units we use for speed is I just think, well, what happens when you see a speed limit if you're driving around? Well, in Denmark and most of the rest of the world, you see things in kilometers per hour. Then I think, well, kilometer is a unit of distance. That's why it's distance on the top. And then per hour, well, that's a unit of time on the bottom. So U is initial velocity or initial speed, which is in meters per second. V then is the final velocity, and that's also in meters per second. Okay, so here we're starting off initially with some sort of speed, and then we speed up, or perhaps we slow down, so then maybe your initial velocity is larger than your final velocity. It doesn't matter, there's no problem there. So that's in U and V, and then we have A, that's the acceleration. And that's going to be assumed to be constant. Okay, so here we're assuming constant acceleration, and that's going to be measured in meters per second squared. That's because it's meters per second. That's because your speed actually changes. Some people like to write actually an acceleration is a change in speed over change in time. That's another way to say it. I mean, this is also correct. Okay, so acceleration is a change in speed over a change in time, or you could say change in, velocity over change in time. So see, you have a velocity, which is in meters per second, and then you divide that by time, which is per second again. So that's why we have meters per second, so that's meters per second squared. We have S, which is the displacement. If we're keeping everything in vector form, we're going to say displacement, which is in meters. And if you really want to do everything correctly, we should actually probably putting little vector signs everywhere here, because these are all vectors. However, we could have them as not vectors if we wanted to. And the last thing is T, which is time. And that's normally measured in seconds, or just S for seconds. So this gives you sort of the main players, so to speak, in these 4 equations of motion. Remember, the last three are actually given in your data booklet, but the very first one isn't, and it's actually very useful. So I often use that one just in solving questions. These are immensely useful. What I like about physics is it actually gives math a purpose. I mean, physics and math are sort of, best friends. In fact, it's hard to do one without the other, well, especially physics. It's hard to do that without math. And that's because we like to quantify things. So things are actually happening and we can measure them and predict what happens. And that's wonderful about accelerated motion, because we can use these simple equations here to solve some situations that might seem really complicated. Like I could say, okay, you're initially driving in your car at a certain speed, and then you slam on the brakes. What will be the acceleration you're going to feel? In other words, are you going to, feel yourself sort of, slamming forward or back or whatever? You could be talking about, if you run into something, how much force will you feel if you run into something? And it turns out the force will be related to the acceleration. And the acceleration is this A term that's in some of these different equations. Now, when I'm solving these equations, I like to teach my students a really easy trick for uniformly accelerated motion. The very first step, though, is to always think, is it accelerating? Because if it's got a constant speed, then it's not accelerating. Right? So this means constant speed here, or constant velocity. And that's because, if you think about it, constant means not changing. And if you look, acceleration means a changing speed. See, acceleration says the speed changes. Well, constant speed, in this case over here, if I have a constant speed, it means I'm not accelerating. So it's a lot simpler to solve these things. So the way that I actually solve these questions, if they're accelerated motion, is to use a nice easy trick, and that trick is this. I like to call it UVAST. It especially works for IB students. Okay, so I call it UVAST. It's not anything brain busting. There's a reason I call it that. It's because whenever I look at a question, the very first step that I do is to actually take a look at, okay, what's the situation? Is this thing accelerating? If it is, then I just think UVAST. And that means what I do is I write down what's U, what's V, what's A, what's S, what's T. I basically make a little table and take a look at what I know and what I don't know, and sometimes what I need to know. Because that's the key thing here. Some things we're given, some information, maybe some information we're missing, and maybe some of it's missing and we don't care. Right? So sometimes it's sort of don't know, don't care. So I'm going to show you an example of how we can actually use UVAST in order to solve some of these questions when we have accelerated motion.
One up, nice. Bumpy side. Nice, from.
It is stream clutch, look. Left is mine.
So here we're going to look at an example of accelerated motion and see how it is that we can use this trick of UVAST in order to solve something. So I've just written out these 4 equations of motion because we might need them. In fact, we're going to need one of them. So let's take a look at some example we could do. This could be just about anything. I could have, well, I was using the example of driving before, so maybe I'll do that. So you're driving your car. So driving in a car. The question is, how long does it take to stop? That might be the question. Okay, how long does it take to stop? Now we're missing some information. And I don't want you to think that physics questions are just you have to be given a bunch of information and what to do. I mean, these are dynamic situations. So try to imagine you're in your car, we're assuming you're driving, and there's clearly some information missing here. So try to think, what information do I need to know before I can know how long does it take to stop? I mean, here I'm asking for time, even though I said how long. That's a common thing that they like to do, right? I mean, we use some terms that aren't always maybe clear. So in this case right here, I'm driving in a car. I might want to know how fast am I going? And then as far as how long does it take to stop? Well, maybe I need to know either how far I drive before I stop, or maybe I need to know, how hard do I press on the brake pedal if I'm driving and I try to stop. So we're going to be given some information. So let's say I want to know the initial speed. So how fast am I going initially? Well, that will be given. So let's just say, so the initial speed will be given as, it doesn't really matter, but let's just say something like 21 meters per second. And then we need to know something else. So here, let's assume that we know how much the acceleration is. So in this case, I know sort of how hard I'm pressing on the brake pedal. So in this case, my acceleration could be, let's say 3.2 meters per second squared. So in that case, I've actually got everything I need in order to solve this. Okay, so I've got an initial speed. So you just have to try to imagine this. Physics questions are actually nice because you can often imagine something happening. And that's what I like about this. So in this case, I'm imagining I'm driving in my car at a speed of 21 meters per second. That's pretty fast, right? 21 meters in 1 second. So I'm moving along. And then I slam on the brakes. And when I do that, I know that my acceleration is this. You may, by the way, want to compare that with the acceleration due to gravity, which is what we call 1g. And that's actually 9.81 meters per second squared. So I'm sort of slowing down something on the order of, well, something close to 1/3 the acceleration due to gravity. So here I'm actually really slamming on the brakes. So maybe I see, I don't know, a deer in front of me that I don't want to hit. So I slam on the brakes. The question is, how long does it take to stop? In other words, I'm looking for the time it takes to stop. So the very first thing then is, well, to look at, do I have uniformly accelerating motion? Yep, the very fact that I have acceleration implies accelerated motion. And it's uniform, it's not changing. This value isn't any different. It's always going to be 3.2 while I'm slowing down. And then so what we can do is use this little trick that I was telling you about called UVAST. So what I like to do is actually write down, like a little table here and say, well, all right, I want UVAST, I want to account for them. The key thing, though, when dealing with questions of this type, this is the most important thing to remember, is to keep track of which way is forward and which way is backwards, or which way is up, which way is down. I always make things that are right or up, those are positive, because I like to think about graphs. When I'm looking at a graph, things going to the right are positive or up is positive. If it goes to the left, it's negative, and if it's down, it's negative. So that's usually the distinction that I like to make. Now when I do this, I haven't been told which way it's going, but I can assume something. Right? If something goes opposite direction to another thing, then I know that it has to be negative sign. I'm going to show you this in context in a second here. So U is my initial speed, and let's assume that you're driving this way. So this is my situation here. I'm driving in my little car. You'll see in a second why it is that I'm not an artist. I don't know, I guess I needed my car to go like this. Here we go. So I'm in my little car here, and I'm initially going with a certain speed, right? I'm initially driving, but then I slam on the brakes until eventually I stop. So the initial speed I can say is positive 21. Now when I write down UVAST, I'm a little bit lazy. I usually don't put in the units. And that's because in my own mind at least, anything that goes here has proper units. That means only meters per second are allowed here and here. Only meters per second squared are allowed here. Only meters are allowed here, and only seconds are allowed here. Which means if I get a question where I don't have those units, I change them before I put them into here. So I actually will convert them. So in this case I have 21 and I'm saying it's positive. The final speed, I haven't been told that, but it's implied. Right? How long does it take to stop? Stop implies that when I'm finished this situation, I'm not moving. So that means this is 0. Now my acceleration, I'm told it's 3.2. So I might be tempted to just say 3.2. This is a distinction here. This is really important. There's going to be something important right here. This is actually wrong. Try to think why. What's missing here? If I made this really 3.2, that means I'm driving this way, and if I have an acceleration of positive 3.2, that means I'm going to start flying forward. You know, I'm accelerating. I've slammed on the gas. Maybe I have nitrous oxide, or maybe, I don't know, I have a rocket strapped to the back of my car, and I'm really going forward. That's not what I want. So how do I mathematically do the opposite? Remember, if I'm going this way, it's like my acceleration is the opposite direction. So I'm going to throw a negative sign on this. That's going to make all the difference. What's my displacement when I stop? I don't know. But I actually don't care. So this is don't know, don't care. And t, that's the time it takes to stop, and that's what I wanted. So I usually put a star. That's just my convention, okay? So when I'm solving questions, you're going to see me use this. So I put a star by the thing I want, question mark with anything I don't know and maybe don't care, maybe I need it, maybe I don't. Let's just see. The good news is, once I've dealt with this, I can reduce this to just a shopping list. Now I'm just looking for a situation where, or an equation, where I have a t in it, and I try to find something that doesn't have an s. Because if it has s, in other words, displacement, I'm going to need an equation. I'm going to need to find that. So that's why just from there, I've got my list of 4 equations. I could use this first one. I could use, well, actually, that's probably the one I should use. It's probably should use v equals u plus at. That's probably the best one to use, right? Because this one has an s in it, this one has it, this one has it. Now, does it mean if I use this, I'd be wrong? No. It just means that I would then first have to find s somehow. I'd have to find my displacement. In this case, though, I'm going to try to take the shortest way to do this. So I think I'm going to use this equation here. It really helps if you're on an exam to actually write down what you're using. So v equals u plus at. Right, that's the equation I'm going to use. Well, then what I do is I just go ahead and solve it. So I know that v is 0, so that cancels out, that crosses out. I want t, and if I have t, that means I can first of all move the u over, so that becomes a minus u, and then I have to divide by a. Now I've done the steps, I've done 2 steps all in one. If you take your time with algebra, you'll see if you go 0 equals u plus at, you can get t on its own by first moving this over, makes it minus u, and then you want to divide by a to get rid of the a. So that's how you do this. So this is the equation I'm going to use. That means I just need to plug in the values. So in this case, negative whatever u is, so that's 21. Divide that by a, which is negative 3.2. Good thing I put in the negative, because if I didn't, I'd end up with a negative time. And as far as we know, you can't have that. Well, not in at least any simple, realistic situation. So now I'm going to use my trusty calculator. I'm going to say negative 21, divide that by negative 3.2. And I get an answer of 3.6, roughly, seconds. So it'll take me 6.6 seconds in order to slow down from an initial speed of 21 meters per second down to a speed of 0. In other words, down to being stopped. So this is how we can solve these kinds of questions. Now this trick doesn't just work for this example, it works for all of them. So anytime I see accelerated motion, I right away start thinking u-vast.
Under.
Man!
It might be a good idea to show you a second example of how to use uniformly accelerated motion. In the last example, we were looking at just something going forward and backwards, but it's also important to understand that you can have this in the vertical direction as well. So I could have an example of, let's say I'm being, let's say I'm being pushed off a cliff. So there I'm going to have a cliff of a certain height. So maybe I'd better write this down. So I am pushed off a, now let's use some units that come up commonly. So something in scientific notation. So let's say 3.25 times 10 to the 2 meters high cliff. So the question is, how fast will I hit the ground? So that's probably not a nice situation for me, but again, in physics, we can, well, we can do just about anything. So in this case right here, that's my example. Okay, so how fast will I be going when I hit the ground? Maybe I should draw a little example here of what's going on. So maybe this is my cliff. Maybe I have some ground somewhere. Maybe I'll draw that sort of green. Now my cliff is going to be 3.25 times 10 to the 2 meters high. And if you remember your scientific notation, that just means 325 meters. So that's no big deal. So right here, this is 325 meters high. So here's me. Now we're going to assume a few things. I've got really long legs apparently. Again, you can see why I'm not an artist. But we're going to assume that I'm at rest when I drop. And we're also going to assume that this is not in 2 dimensions. In other words, I don't have any forward speed. I'm just dropping down. If you've ever seen old cartoons like with Wile E. Coyote, you know, he would walk out of a cliff, you know, sort of be hanging in the air, and then look down, realize it, hold up a sign usually that says, you know, help, and then he would fall down. Obviously, that's not what happens. Gravity is always acting on you. It's acting on me right now, you know, pulling me down. So because of this, then, I'm going to actually fall straight down. So I'm going to do, well, that actually looks like I'm peeing, so maybe I shouldn't do that. I'm going to go down. That should be pretty obvious. But the question is then, what's my speed when I hit the ground here? So this is going to be probably, ouch. So we're going to have to calculate this. This is a very nice example of something that's very friendly for using UVAST. So you remember those 4 equations of motion. These are these 3 that are in your equation booklet or your data booklet, and this first one here, which I suggest memorizing. So if we take a look at this then, we have a situation where it helps to figure out, well, what's going on? So I'm going to write out U, V, A, S, T. And this way, I can use this to try to tell what my different variables are. Whoops, I drew a line through my U, but hopefully you can forgive me. So my initial speed, remember that's what U means. U is initial speed, is 0. It's implied that I'm at rest when I fall. By the way, I could have easily made this something else. This example could have been, I initially have an upward speed of blah, blah, blah meters per second. No problem whatsoever. Just put that in. Just make sure it's positive because you're going up. The question could have also been, you know, I'm being thrown down with the speed. Well, then I would just put a negative here. That's it. That's how you deal with these questions. It's not more complicated than that. So in this case then, V, that's the final speed. That's what I want. So I'm going to put a star by that. Now the acceleration here is a little bit different because it's not told, but it's implied. Right? I'm on Earth, I'm assuming, because the acceleration due to gravity is different on different planets or different places. Even it's different depending on how far you are from the surface of the Earth. Actually, technically, it's the center of the Earth. But luckily, it doesn't change much, so it's not like gravity changes much when you're on the top of Mount Everest. Just for fun, in my class, we calculated that, and it's nothing you'd ever notice. So gravity works just fine anywhere on the surface of the Earth. So because of that, then we're going to know this value for acceleration. And it's going to be negative 9.81 meters per second squared. This is maybe not very clear with my, I didn't give much space here, but this is negative 9.81. That is the acceleration due to gravity on Earth. Okay, that's this value right here. This happens anytime you're working with something on Earth. It's 9.81 meters per second squared. Now, the reason I put a negative is because I accelerate downwards. I'm not going to be dropped and go upwards. If so, then it will be positive. So keep that in mind. Remember that up is positive and right is positive. Left and down are negative in my own conventions here. But I think that should make sense, right? Because when you're doing a lot of math, we use the same convention there too, with graphs. Now, what's my displacement? You have to think, I start somewhere, and when I land, I am lower than when I started. So this is going to be a negative value, and it's negative 325 meters. I could, of course, say 3.25 times 10 to the 2, same. The reason why scientific notation comes in really handy is for really large numbers or really small numbers. In this case, I rather look at 325 instead of this. It's the same thing though. And the time it takes for me to hit the ground, I don't know. And in this case, I don't care. So I'm going to put a question mark by it. Now the question could have been, how long will I be in the air? Then I could easily calculate that. So now I have to use UVAS to try to figure out which equation should I use. So if you take a look here, I've got an equation that I need to find V. Okay, I need to find the final
Deagle
speed,
if you can't use it?
and I want to avoid having a T in it, because if I use an equation with a T, then I'm going to have to find that time. So in this sense, then it becomes really easy because there's only one equation without a T in it. Hopefully you see it. It's the fourth one. So I'm going to write that equation down. V squared equals U squared plus 2AS. And then I just start filling things in. Well, U is 0, so that's easy. That goes out. And actually, I want V. So in this case, I made it really easy, I guess. Maybe I should have made it a bit tougher, but oh well. In this case, then, if I want the velocity, or sorry, the final speed, then what I should do is, well, I want to undo the square. So I take the square root of both sides. And that'll give me square root of 2 times A times S. Technically, it should be plus or minus. That's the mathematical solution, but the only physical solution that makes sense is a positive value for speed. However, well, this is what we normally say. We normally say a speed here. If I wanted the vector, then I would actually say it was, this many meters per second down. But I asked how fast. I didn't say what's my velocity. This implied a speed. So I'm going to be a bit lazy and just find V here. So it's just going to be, well, the square root of 2 times negative 9.81 times negative 325. And thank goodness that I did this right, because the negative and the negative, they cancel each other out and give you a positive. That's good, because if we had a negative value we were trying to take the square root of, then we would have a non-real answer. And it doesn't mean it's not doable. It just means you have to use a different set of math tools to do it. And you have to look at, well, non-real numbers. So those are called imaginary. But we're not going to worry about that. I'm just going to calculate this. So 325 times 9.81 times 2. I just did a little bit backwards. I'm going to take the square root of the answer. And I get 79.8529, blah, 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 blah. So I'm going to use the same number of digits that I was given here. So here I use 3 numbers in order to write my answer. So I could say it's 79.9 meters per second. I could also write it as 7.99 times 10 to the 1. It's the same thing. But I'm just going to keep it at that. So this is going to be my final answer. Now, I always like to think about, does this make any sense? You should always take a look. Whenever you're calculating speeds of things, when you're done, you need to never be anything greater than the speed of light. So as far as we know, nothing can go faster than c. So that's 3 times 10 to the 8 meters per second. So that's not that fast. But try to think about how fast this really is. This is about 80 meters in 1 second. We can, of course, we can convert this if we want to kilometers per hour. There's no problem there. So what I can do then, let's say I wanted to convert this. This is another skill I think that comes in very handy with students. So I'm going to convert it. I'm going to say V equals 79.9. And I'm going to say meters on the top and seconds on the bottom. Now what I have to do then is try to look at different units and things that can actually cancel out my meters and my seconds, because I want kilometers per hour. So I know that there are 1,000 meters in 1 kilometer, And the reason I put the meters on the bottom is because I want meters on the top and meters on the bottom to cancel out. And there's 1,000 meters in 1 kilometer. So now if I did this, just this divided by this, I'd have kilometers per second. But I want something a little bit different, so I want to actually try to take this and figure out, well, there's 3,600 seconds in 1 hour. And it turns out then the seconds cancel out. So all I have to do is just multiply these. So 3,600 times 79.9. Take that number, divide it by 1,000, and I get around 287 kilometers per hour. That is actually pretty fast. Okay, but this is still, it's still possible to do this. You see, we are actually still able to solve this, and we can just use UVAST. It's actually a very nice, simple, nice way to solve these equations with uniformly accelerated motion. In this case, because I was dropping off a cliff, I was accelerating.
Go away.
In the last example, we were looking at someone that's falling, well, me, being dropped off a cliff and landing on the ground with a really high speed. It was like 280 something kilometers per hour. And I just wanted to tell you something about that, is that value, it actually isn't exactly true. So here we were calculating that example based on having no air resistance, which means when I'm falling through the air, we're assuming that there's no air resistance, so then I could keep accelerating. But in real life, of course, there's something else. There's air resistance. So I would have actually been going slower because I would have reached terminal velocity, which sounds really dangerous, but actually just means I can't accelerate anymore. So we're going to be doing a video that talks about that in more detail a little bit later. But I just wanted to make that clear. So now it's time to take a look at graphing, because that's something that comes up very often on exams, but it's also a really nice way to see physics and math coming together really nicely. So in this example, it doesn't really matter what I consider. This could be, let's say, well, my last name is Campbell, so I liked to do this little experiment in my class where I would actually take a can of soup and I would roll it up a hill. Okay, so I roll a can of Campbell's soup. That's a type of soup. And we'll say up an incline. In other words, some line that is inclined. In other words, some sort of hill. Maybe I shouldn't be doing that gesture too much, but this is something that actually goes up a hill like this. There it is. There's my little can. And what I do is, of course, I give it a push so it goes up the hill. And what I would do is put a little detector at the bottom here. Okay, so the little detector, it detects the distance from the can to itself every second. So it's kind of neat. It does a little sonar thing. So you could actually have this on a little stand. Basically, I would roll the can up the hill. And if you know anything about hills, you know what's going to happen. You don't even have to be a physicist to understand this. The can is going to go up the hill, and it's going to slow down. It's going to stop, and it's going to roll back down. So let's take a look at what the graph of displacement versus time would look like. Okay, so there I'm going to show you that graph here. So maybe I'll try to graph it nicely here. So there'll be displacement versus time. And remember, displacement is written with this letter here. I'm going to actually leave myself a bit more room here. Sorry. I'm going to make this actually positive for now. So what will happen is at time t equals 0, this will be in seconds, and this is going to be in meters. So at 0 seconds, my can is at the bottom, so there it is. Now at some point, it goes, as time goes by, it's going to go up the hill, which means it's going to get farther away. So in this case, at some point in time, it's going to have some sort of maximum height. Maybe that's this, like whatever this distance away is. That's going to be its distance here, from the start point. Keep in mind it's projected at an angle, but I don't really care too much. I just want to show roughly what the graph does. Now, of course, it starts here with a speed. It eventually stops at wherever it stops. It eventually reaches its own maximum height. Then it comes back down, which means the distance away gets smaller again. So if I made this this many units, then it would reach the ground again at this time here. It has to be symmetric. And that means the curve is actually going to do this. And the cool thing is, if you did this with this little type of detector, you really do get a graph that looks like this. Well, that's kind of cool. But even better is taking a look at the next two graphs. So there I'm going to take a look at the velocity of this can as a function of time. So I'm going to graph that now, right here. So there I'm going to graph time in seconds still, but here I'm going to have velocity, which is in meters per second. I'm going to maybe put a little vector symbol on top of it. Maybe I should separate these. That's fine. Well, yeah, I better put a line here just to make sure that we know that we're on a different graph. Although, actually, that may have actually made things look more complicated. But, oh well. So if we take a look at this example here, what I can do is take a look at this point when it starts. How fast is it going? Well, it has a positive speed. I don't know what the speed is, but it's something positive. So I'm going to arbitrarily put it maybe here at whatever some value it is. Now at some point, of course, at the top, its speed is 0 because it stops. So that means, remember, this graph looks at speed. So that means at some point the y value is going to be 0. And that happens precisely when this right here happens. So take a look at this. It's going to happen exactly here. I did a dotted line so that I could make sure that these two line up. And then, of course, at another time, it's going to actually be negative. So it turns out that's because it goes back down the hill. So if I was really good at drawing straight lines, this would actually be a perfectly nice straight line graph of the velocity. So this is what the velocity would do. And furthermore, I can go one step further and say, well, what does the acceleration look like? And it turns out that's going to be really good because, well, it's going to be easy. So it's going to be in meters per second squared. I'll just get out of the way so you can see it. So it's going to be in meters per second squared. And in this case, it's going to be just some negative constant value. Ideally, it'll be something negative here. And if you have the right kind of lab conditions, you can actually have this value right here be negative 9.81, which is kind of neat. In other words, that would be the acceleration due to gravity. It's not always exactly negative 9.81. It's actually maybe something different. But the key thing to look at here is, what do these graphs actually do? Okay, so the key thing here is that the graph does this shape here. When it goes up, it does this shape right here for its speed. And it does this shape right here for its acceleration. Now, the reason I drew these like this is dependent on the situation. So if I had a different situation, maybe I'm driving in my car, the graphs won't necessarily do this. So why did I bother showing you these graphs? It's because these three graphs are related to each other. And this is where calculus comes in. Although the IB physics course is not supposed to be a calculus-based course, but this is calculus. I'll show you that. So calculus is all about looking at either the slope of a graph or the area underneath a graph. Now the slope, some people call it the gradient, but it doesn't really matter. You can call it the slope or gradient, doesn't matter. As the Danes say, delimal. So it doesn't matter at all. So the slope doesn't matter whether you call it gradient or slope, but what's important though is taking a look here. If I take a look at this very first graph here, I can take a look at what its speed was, and I can get the speed graph based on how the displacement graph looks. In other words, if you give me a graph of displacement, I don't even have to know the situation. I can draw this graph. And that's because I know how velocity is related to displacement. Velocity is just a change in displacement. Some people write it as V equals delta S over delta T, which means a change in displacement over change in time. So what I can do then is take a look at this and say, well, that means that any time, this is a nice trick that I like to use here, is that any time I go down in a graph, so to speak, okay, what I mean by that is if I start with a displacement graph and I want the velocity graph, I'm going down, so to speak. Same thing will happen if I'm given only a velocity graph and I'm asked for acceleration. Then, in a sense, I'm going down. If I've drawn these three graphs, displacement, then velocity, then acceleration. If I go down, I take the gradient, or slope. Right? That's what it's sometimes also called. Now, if you want the calculus word, this is actually called the derivative. So I use the calculus word, but it's not a bad thing. It's just called a derivative. So if you know calculus, you can actually find an equation for the derivative. But if you just want to draw it, which is, you are expected to be able to draw these kind of things and use them in the physics SL class. So just keep in mind, going down means take the gradient or the slope. Can you see right here that if I had a little line, let's say I'm looking at the gradient of this curve at any point. Over here the gradient is this. It's like that's what the slope is doing. Over here it's a little bit different. Over here, however, it's flat. Over here it's down. Over here it's steeper down. I guess I should do it like that. So that means at this point, look at the slope here. The slope is all about, a change in height over a change in time. In other words, rise over run, some people call it. So that means here, at this point, the slope is 0. So that means the value of the velocity is 0. Do you see over here at the beginning? The slope was some positive slope, some value. Who cares what the value is, but it's some positive value. So look over here, I make y a positive value. Of course, the slope gets less and less as I go along, so the value gets less and less. And it goes all the way like this. Because, of course, it comes back down, so there the slope is negative. And it's a negative not very big number over here. Over here, it's a bigger negative number. Over here, it's even bigger negative number. So see, it's an even bigger negative number. And I can do the same thing with the acceleration. So in this sense right here, as I go down, take a look. This one right here is the acceleration is just the slope of this graph. Well, take a look. The slope at this point is this. The slope at this point is this. The slope at this point is this. Because the slope never changes, it's always some constant negative value. That means the acceleration will be some constant negative value. Now, conversely, we can do the same thing by going up. Okay, so in this case right here, if we go up, there we take the area under the curve. In other words, if you want calculus terms, we actually do what's called the integral. So what that means is, let's say I'm given a graph of, I don't know, velocity, and I want to find the displacement. I just have to take the area underneath that curve, whether it's positive or it could be negative, it could be here, it could be here. So that's how this stuff works. You can use graphs in order to tell you what happens, and the graphs are all related to each other. As long as you write a displacement, velocity, acceleration graph, then you can actually figure out what's going on.
Mid-rush.
In the last example, we looked at graphing and how we can actually have a graph of displacement versus velocity versus time. And we can use those graphs to tell what happens. And I thought maybe it's a good idea to give you a more practical example, so something with some numbers in it, because this can sometimes be a challenge for students. So I can have an example where I have some sort of graph drawn. And the graph will be given, let's say, a velocity versus time in this case. So I'm going to just draw some sort of graph of velocity versus time. I guess I need some axes here. So there's my time in seconds. And I'm going to make my velocity go from, let's say, by the way, this is going to be velocity in meters per second.
Why do you even shift?
Okay, that's important, that I have my velocity in meters per second.
Use your brain, man.
What I'm going to do then is take a look at what this graph does. So let's assume that this graph does something like, let's say this is 1, this is 2, this is 3 seconds. And I'm going to have this value be 2.5 meters per second and 5 meters per second. the axes don't have to be the same scale. So in this case, this should still work.
But if you come from heaven?
Now what I'm going to do then is give you a drawing. So maybe it starts off as 0, maybe it goes up to this point. So it does something like that, and let's say it does something like this. This is meant to be straight line.
Wow,
so
nice.
This is a velocity versus time graph. My T didn't really look very much like a T, did it? It's kind of a lousy T. So there we go, so velocity versus time. Now the question could be asking, maybe I want to know the acceleration. So what is the acceleration at, it could be anywhere. I could make it T equals 2 seconds. Question mark. This could be the question here. What's the acceleration at a time T equals 2 seconds? So what I can do then is take a look at this. Okay, well, I'm given a graph of velocity versus time, and I want acceleration. So you remember that little trick that I gave you? That if you had S or V or A, graph of each of these, if you go down, it's the slope, and up is the area under that curve. So if you remember that little trick, then we can actually do this. The acceleration at t equals 2 seconds is fairly straightforward to do then. All I have to do is realize I start with a velocity graph. I want acceleration. That means I'm going down, and that means I have to take the slope of it. So if I want the acceleration at time t equals 3, I need to know what is the slope of this graph at exactly t equals 3. So in this case, 2 seconds. 2, not 3, 2. So at time t equals 2, that's right here. Take a look at what this graph is doing at this point. This graph is horizontal, right? It's right here. If it's horizontal, that means that the slope is 0. So that means the acceleration then equals 0. I suppose you could say meters per second squared, but it doesn't really make much sense to put units on something that's 0. So I'm going to say the acceleration is 0. There's no acceleration. But is it moving? Try to think about this. This is a graph of velocity versus time. At time t equals 2, its velocity is 5. That means it's moving with a speed of 5 meters per second somewhere. So it is moving. So that means you can be moving and not accelerating. And in this sense, that's exactly what's happening here. If you're ever driving in your car, you know that you can be moving without accelerating, because you could be driving in your car at a constant speed, let's say 100 kilometers per hour. And that means you're not accelerating, but you're still moving. So it's okay, you're still allowed to be no acceleration, even if you have some movement. And B, maybe I want to ask another question. Maybe I want to ask for the distance traveled. So what is the, in this case, I can actually say, yeah, since I didn't say velocity, I said it was only the speed here. So I'll say, what's the distance traveled? Let's say in the first 3 seconds. Okay, so what's the distance traveled in the first 3 seconds? So that's what I'm asking for now. So if I want to know the distance traveled in the first 3 seconds, what I need to do then is think again about this graph. I have a velocity versus time graph. In other words, I'm here. I want to know the distance or displacement. So that means I want this one. Remember, S means distance or displacement. And if I want this one, I went from here to here. That means I need to take the area under the curve. So in that sense, then, I can sort of see this as like 2 different little areas here. I need to find out what this area is. I can see it as 2 different shapes. I can see it as that one shape and that other shape. Hey, that should work. Now, if you look at this, I'm just finding the area. I'm not using any fancy calculus tricks, even though what I'm really doing here, I'm taking the integral. Okay, so that's really what I'm doing here. And if you knew the equation for this mathematically, you could figure out that answer in a few seconds. But it turns out you can also do this. And this is just fine. You can totally take the area under this. I made this straight lines on purpose, because if this was a curved thing, it's a lot harder to get the area. And then you have to maybe start using some tricks like how many triangles do you use and how many squares do you use? It turns out that's the basis of calculus and integrals, is that you can find the area underneath some sort of curvy curve like this. If you want to find that area, just take a huge number of little rectangles, and as long as you have enough rectangles that are small enough, you'll get the area. And that's precisely what an integral is doing. But in this case, we're going to keep it nice and simple. Just wanted to explain where the link is with calculus. But in this case, I want the distance traveled, so I take the area of these two little shapes. So what's the area of that shape? Well, it's a triangle, so I can find that area. That area is going to be, let's see, well, it's this has a value of 1 here, and it has a height of 5. Keep in mind this is 1 meter, and this is meter per second. So what's going to happen then is if I want, whoops, this isn't meters, this is time. This is seconds. So this is meters per second times seconds. So in this case, that's what we have going on here. Now, if I want to take the area of something, what I would do then is multiply the base times the height, and I would divide that by 2. That's the area of a triangle, of a right angle triangle. So in that sense, then I'm going to do 1/2 of 1 second times 5 meters per second. And then that answer, well, that'll be just 5 divided by 2, so that'll just be 2.5. And let's take a look at the units. I have meters per second times seconds. The seconds would cancel out, so I just have meters. Is that a proper unit for distance? Yep. But that's how I know I did it right. So that's also important, is to look at unit analysis. You can take a look at the units of what you're looking at and make sure they make sense. Now, I'm not done yet. That's just one answer. I also need the area of this rectangle. So what's that area? Well, that area has a length. Now, keep in mind, it's not a length of 3. It actually only starts at 1. So because it goes from 1 to 3, its length is actually 2 seconds long. It's weird to think that something has a length of 2 seconds, but it does. It's hard to draw that, but it just means it lasts 2 seconds. And what's its height? Its height is still 5. So 5 meters per second times. Linearization is something that may not be an official thing you have to learn in the physics SL course, but it's something that comes up so often, and it's a skill you're expected to have. I find it's really worthwhile to cover it now. It's especially common on paper 2, question A1, the very first question on paper 2. Very often will have some weird situation you've never heard of. They'll give you a graph, and you're expected to do some things with that graph. For example, yeah, say what you could graph against what to get a straight line and what the slope would be. And this is precisely what we're going to do here. So first of all, when linearization, that just means make something linear. Make something like a line. So when we talk about linearization, we're just looking at this equation, y equals mx plus, some people say b, some people say c. It doesn't matter. The key thing is this. In this sort of situation, you've got some sort of graph, right? You've got an x here, you've got a y here. So the y and x have to actually be there. But then whatever this m is, that's the slope or the gradient, depending on where you come from. I know in the US we were taught that it's called the slope, but I know in England, for example, they sometimes call it gradient. It doesn't matter. As far as this b goes, or some people write it as a c, doesn't matter. There we're looking at a graph. I better actually make this one here a little bit lower, just so that you can see it. I realize it may be off the screen. So I'll make it like this here. So if I've got this sort of graph here, then I could actually think about this is x, this is y, and then I would have some sort of graph. Let's say it's like this, some sort of straight line. So this straight line here, that slope would be m. Right, that would be the gradient here, the rise over run. And the b value here, that would be the y-intercept. In other words, if you make x equals 0, right, that means this whole thing cancels out. That means y equals that value. So that means when x is 0, this means that's the y-intercept. So that's B. Just to remind you at least how we work with these graphs. Now I could give an example. So the example could be something like, y equals 2x minus 1. This is a really simple, maybe really stupid example, but I think it bears doing quickly. So if we want to actually graph this, we could actually do it. We know that the slope is 2, and we know that the y-intercept is negative 1. So because of that, what I can do then is, well, assuming this is 1, 2, and 3 here, and this is 1 and 2, and this is negative 1, this is negative 2, and so on, then I could say, well, at negative 1, I have a y-intercept, so there it is. And the meaning of slope means that for every 1 unit I go to the right, I go up or down by whatever value that slope is, which means from here, I go 1 to the right, and then I go up 2, because the slope is positive 2. So I go 1 right, up 2. I can go 1 right, up 2. And if I was good at drawing straight lines, which I'm not, I could draw a straight line through these. It's a bit curvy. That's what it would look like. Super stupid example, yes. But now I'll give you something a bit more practical. So what if, maybe I'll divide the board a little bit here. So what if this time we're given a situation where now we're actually doing an experiment with springs. So this could be something like we're maybe trying to look at this relation. This is called Hooke's law, which relates the force on a spring to its displacement x, and k is just a spring constant. Now this negative, it's there to denote that the direction of the force is opposite to the displacement, which means if I stretch it this way, the force, it wants to go that way. So the negative isn't going to be so important. Okay, I'm going to actually ignore the negative. But if you actually did an experiment of this, so you actually sat down and you had a bunch of different maybe weights that you put at the end of a spring. Okay, so you had some sort of springs. So like this, there's a little spring, and you've got a little weight at the end of it. And if you knew what its mass was, and then you knew how much it was displaced, this would be x here. And then if you put more weight on it, it would displace more. If you did that experiment, then you might have data points that look like this. You know, you'd have things, you'd have values here. I don't need to be that precise because I'm just trying to show the idea. So if you graphed, you know, your different data points, so there's an f versus x here, there's another f versus x data point. You could think, well, what do I have to graph against what to get the value of k? This is a very common type of thing you want to do. Right? You want to find out what's the spring constant. You could actually say, fine, I'll just find the spring constant for this f and x pair, and I'll get a k value, and then I'll do it here, and I'll get it here. I have a bunch of different k's, and maybe take the average. But a much better way to do it is to do a graph. It's the whole reason we graph this in the first place. So in this sense, if I graph stuff against stuff, maybe I can be clever and graph the right things in order to get something meaningful. And in this sense, this is why we're going to linearize this, which means I'm going to see this as a straight line. I'm going to see it as a y equals something times x. So take a look then, if I did a graph then of x and f, this will be in newtons and this will be in meters. If I graphed f versus x directly, that means f is like my y, my x is, well, my x, that's nice, and that means my k is the slope. And because I don't have a plus b, I don't have a plus anything here. So this means the y-intercept in this case would be 0. So that means I expect it to cross through the point 0, 0, or the origin. And I would expect it to have some sort of slope. Now whatever that slope is, that slope will be k. Isn't that cool? So if you can graph f versus x, then the slope will be k. That's easy because you have a bunch of data points and then you draw a line of best fit through them, and you can actually say, well, that slope of that line of best fit, that's k. You can even go further and say what's the uncertainty on that slope, right, by looking at how much it can go up or down, and that gives you an uncertainty on k. So you could even say k equals blah, 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 plus or minus something. So that's really useful. But what if we have an even more complicated looking example? What if we have something like this time a pendulum? Now the equation for a pendulum, if I remember it right, it's t equals 2 pi times the square root L over g. So this could be another example here. What I mean here is we've got some sort of thing here that's actually oscillating back and forth. It could be anything. Okay, so this right here could be an experiment where, well, we would have a different value of length. We'll put that in meters. And we would have the period. That's what t means. T is the period, which is in seconds. It just means how long it takes to go back and forth once. This example, this could actually be, I mean, you could be doing anything, right? You could have different lengths of pendulums. This could be a bunch of cats. And if you have a bunch of cats of different lengths and you let them oscillate back and forth, hopefully you're not hurting them, then you could actually do this experiment. So a bunch of different cats of different length, and you measure the period of oscillation for them. That means if you graphed just, let's say, t versus L here, you'd actually have a graph that looks like this. And the problem is then, how do I find the slope of that? What does it mean? This is not very useful. It's doable. You could totally graph this. But the problem is, this is a curvy thing. See, I don't want to graph this. By the way, the reason I know that, because g is a constant, 2 and pi are constants. So this t varies as square root of L. So this is a graph of t versus L, and a square root graph does this. Just that's how I knew that shape. But what I can do is linearize this one. I could try to take away that square root. So by doing that, I could actually take a look and maybe I square both sides. That means I get t squared equals 4 pi squared. Don't forget, you have to do 2 squared pi squared times L. And I can just write the over g here. Take a look now what I've just done. Now, this may still look really weird. And then you might think, why in the world did I do this? That's because this, now by itself, that can be my y. This can be my x. And this junk here, okay, so this junk right here, all this right here, that's going to be my slope. So that means if I graphed, instead of t versus L, which is not very helpful, what if instead I graphed t squared versus L? Then I've just linearized this. You see that now I've just figured out what I have to graph to get a straight line. And if I do that, I expect, by the way, there's no plus something or minus something on this equation, so I expect it to pass through 0, 0, and that means it's going to have some sort of slope. And the slope now is not going to be exactly equal to g, because by the way, you can do this experiment to find what the acceleration due to gravity is. If you've done your experiment sufficiently accurate, so maybe you really tried to minimize your systematic and random errors, if you do it right, you should get a g value of roughly what the acceleration due to gravity should be, which should be 9.81. Now the slope will not be equal to g, right? The slope will be 4 pi squared over g. But if you wanted to find g, then you totally could do it, right? Because g, if I did this, I could just get g on its own and just basically switch it with the slope. So g comes up here, slope goes down. That means g would be equal to 4 pi squared divided by the slope. And that's useful. You see that just from that, from my graph, then, by graphing t squared versus L, instead of just t versus L, I can actually get something that's useful. I can take that slope, and that slope can get me g, because g is related to the slope. So hopefully you see how useful this skill can be, of this linearization. This helps not only in physics, but also helps in math. It doesn't just help on paper 2, question A1, although it commonly comes up here. Right? They often ask, what could you graph against what? Or what would the slope mean? Or sometimes they say, what would you graph to get g? And you would just explain exactly this, and you'd be fine. But it also comes up on other exam questions, and I think it's just a useful thing, and a useful way to mix linear graphs with physics.
Kick your little pussy, cunt.
You can suck my dick if you like.
Yeah, but it's very small, I wouldn't be able to catch it.
Yeah, okay, yes.
Sorry, but I can't suck anything that's below microscopic level.
It's also important in physics SL to talk about forces and Newton's laws. The very first thing I want to do with forces is just explain a bit about free body diagrams. I think those are a useful way to draw things. So let's say if I have a free body diagram, what I might do then is just draw something, or draw a situation where I draw what forces are acting on that body. So that could, for example, be me right now. Right now I'm standing on the ground, and there are clearly forces acting on me, even though I may not feel it. If I've been on my feet for a long time, clearly my feet will hurt. So this gives me some indication of what's going on. But the force that's always acting on me, first of all, is gravity. And gravity is always acting down. So I'm going to draw a different colored force. So normally we draw the forces going from the center of whatever body we're looking at. So this would be the center of mass. In this case, I'll label it F with a little subscript G. The G means gravity. Now, of course, if that was the only force that was acting on me, I'd actually be flying downwards. And the fact that I'm not tells me there must be another force. And it turns out there is an upwards force as well. And that's what we call a normal force. So I'll label it F with a little n. Now, at the moment, that normal force going upwards and the downwards force, they're equaling each other out. In other words, they're equal but opposite directions. And as a result, because they balance each other out, then I'll say this, that if F net equals 0, then there's no acceleration. This is going to be something important later, so I'm sort of hinting already at some of Newton's laws. But basically what it means is, well, I mentioned force, and then I mentioned acceleration. I'd better define force a little bit better. Force is a push on something. Force is measured in different units, but the most common one is to measure it in newtons. Okay, that's the unit for force. However, it can also be kilogram meters per second squared. We'll see a little bit later why that is. But as far as forces go, those are really important. Now, what we can do in any situation is draw a free body diagram to figure out where all the different forces are going and what the resultant will be. So in this case right here, when I say a net force implies adding up all the vectors. Okay, so for net force, so F net equals add up all the vectors. So if they all cancel out, I made a really bad A there. So if all the vectors cancel each other out and the net force is 0, then you have no acceleration. And it turns out that's really nice to know about. And it turns out you can figure out what is happening in a situation just based on those forces. So I could do an example. Here we go. So let's say my examples almost always involve some violence of some form on me, just because it's more exciting than just a box sitting on a table or something rolling down a hill. So in this case, I am attacked by sharks. Actually, I'm going to be pulled by sharks. What is the resultant force? And a lot of times we're going to mention either resultant or net. Those are going to mean the same thing. I'm just going to try to separate these things just so it's a little bit more clear here. So what is the resultant force? So let's say I'm swimming in the water. Maybe I'll get a blue marker here or chalk. So here's some water. And let's say, so here I am. I'm bobbing in the water. I'm not very happy because I'm about to be eaten by sharks. It's maybe not a very nice situation, but I always liked watching Shark Week on TV, so of course sharks don't always attack people, but in this situation, I'm being pulled by sharks. So the question is then, well, what are the sharks doing to me? Well, at this point, I'm not going to draw sharks because I'm not a very good artist. But what I can show you is maybe which way the different directions are going. So let's say one of the sharks is giving me a force of, I don't know, 10 newtons to the right. So I'm going to draw that force. So from the right, so from the center of my mass, I'm going to draw an arrow that is 10 newtons long. I'm going to assume this is east, by the way. Or actually, I'll just say, yeah, I'm going to assume that's east. Okay, so that's going to be that way. I drew it exactly 10 newtons long. How do I know how long 10 newtons is? I draw whatever length I want and I label it, and now it becomes 10 newtons. So that's one force going to the right. If that was the only force, then this would be a boring question. The resultant force, or the net force, is just adding up all the vectors. So I'm going to add another shark. Maybe I'll add one that's maybe pulling me south at 11 newtons. So I'll make that arrow a little bit longer. Okay, and that one right there will be south. So this is a shark now that's pulling me. Let's assume this is sort of in 3 dimensions here. So I guess this is south. That'll be north, east, south, and west. And let's assume that a third shark is pulling on me. This one, let's say it's I don't know, 18 newtons to the west. So I'm going to make it much bigger than my last one. This will be 18 newtons west. The question is then, what's my resultant force? The reason we bother figuring this out is actually because this can tell me about the situation. This can tell me about what's going to happen to me, which way I'm going to go, for example. Because I'm going to be pulled now. I'm being pulled in 3 directions. So what I need to do then is find the net force here. Okay, the resultant or net force just means add up all the vectors. Now we add up vectors head to tail, and it doesn't matter how I do it, but what I can maybe do is start off by simplifying my problem a little bit. See how this east one and this west one are acting opposite to each other? That means then I can just subtract them. So the one that wins is 18 newtons. That's like a pull way more this way than it is that way. So the result of that one, at least, the 18 minus 10 equals 8 newtons. So what this means is I can rewrite this question, which looks complicated. Now I can rewrite it as just this. I have one arrow then going west. That's 8 newtons long. That's because 18 minus 10, the result is only 8 newtons west. So I've only got that. And if I want to add up vectors, this isn't very useful. I need to pick up this vector, so to speak, and move it. So I'm going to move it right here and attach it. So it's like I go left and then I go down. Now I have to go down by 11 newtons. When I say down, that's south. This is west. So then the resultant force is quite simply just what's the start and end and which way do I go. So this direction right here, that's going to be F net. And we've done an example like this before, where what we can do then to find F net, well, we know that F net squared equals 8 squared plus 11 squared. Therefore, I can say then that F net is going to be, well, it's going to be the square root of, 64 plus 121. So I'll just figure that out right now. Okay. Because I need to do the square root of those.
I got B.
And the result is, what, 13.6 approximately. Although I only did give 2 digits in my answer, in my questions, so I can probably only say 14 newtons. But the problem is, which direction is this? Where does it go? Well, I know it's sort of, I mean, a lot of people just say southwest. But if it's southwest, that implies it's exactly 45 degrees. It would only be 45 degrees if these two were equal length. If it was like 8 and 8 or 11 and 11, then I could say southwest. But unfortunately, it's not exactly like that, so I need to figure out this angle. The angle between where I started and where I ended up. In other words, I end up over here. I started here, end here. So what I can do then is figure out that angle. We did this before. I could say then that, let's see, tangent of theta. Tangent is going to be opposite over adjacent, so it's going to be 11 over 8. And then what I can do then is just take the inverse tangent of that. And that'll give me theta. So let me just get out my trusty calculator. And what I'll do is actually calculate it. So 11 divided by 8, and I take the inverse tangent of that answer.
Come here, Green.
And I get an answer
Green,
of 54 degrees, pretty much 54.
Get in and watch.
So then I can say it's west 54 degrees south, because I go west first, then 54 degrees south, so that could be my answer. Or I could also try to figure out the bearing. So this right here, by the way, could be my answer. Or I could actually figure out the bearing. Now, if I know that this angle right here is 54 degrees, bearings are always done from north and then all the way around. Right? So then what I can do then is calculate then what that has to be. This will be, I could say there's a number of ways of doing it here. But what I could do is actually say, well, all halfway around, that's 180. And so what I could do then is say that, well, this little piece right here is going to be 36 degrees, right here. So 180 plus 36 is going to be 216 degrees. So I could also say that it was equal to 14 newtons at a bearing of 216. That's another way of saying it. It doesn't really matter too much how you define the angles. What matters, though, is understanding that we can figure out the result by looking at the net force. The resultant force. This tells me I'm going to be going that way. Newton's laws come up a lot in a physics course, but first I wanted to talk about equilibrium. I mentioned it a little bit earlier. I just want to make sure we sort of firm it up what I mean by equilibrium. Just gotta find my chalk. Equilibrium is when the resultant force is zero. Whoops, my R looked like a V there. So resultant force equals zero. In other words, the
they can see my stream. I don't have delay in my stream. You don't need to give them info.
Equals zero. That's the key thing here. Okay, so if you're in equilibrium, it means that the forces acting on you are canceling each other out. So you still might have forces. They're just evening each other out and canceling each other. And that's when you're in equilibrium. But I want to point out one thing. Really important. You can still be moving.
Nice.
Like a lot of students think as soon as you have a net force of zero, it means that you're stopped.
Orange.
But you can still be moving.
Orange.
I mean, right now, as I stand still, right now, my net force is zero because I have a downwards gravitational force and an upwards normal force. So I'm not moving, and my net force is zero, so I'm in equilibrium. Often it's called translational equilibrium.
No, it's okay, man, thank you.
Because you could also be in rotational equilibrium. But here we'll just talk about translational equilibrium, meaning the net force is zero. So they all cancel each other out. But you can have an example when you are moving. So like, what if you're in a plane? So this is my little plane here. Let's see here, a little crappy propeller plane. There's my wings, and there's my little plane here. There's my tail. So here's my little plane. That's not a very nice plane, but this is supposed to be a propeller plane. When you're flying through the air, you have a forward force, which is called thrust. You have a backwards force, which is air resistance in this case. You have a downwards force of gravity, and you have an upwards force of lift. And so when you're flying, you could be in equilibrium, meaning you're still moving. Your net
man.
Speed can still be moving.
Nice.
Run.
But in this case right here, we still have F net equals zero. But here we have a V which is not equal to zero. See that? So here we are actually moving with some speed. We're actually flying through the air happily, so, but our net force can be zero. And of course, by making one of the forces larger or smaller, we can adjust how we fly. That's one of the main things behind airplanes. Of course, it's a bit more complicated because there's surfaces like on the ends of the wings called ailerons that move up and down. But the main idea is just that the net force can be zero, and you can still be moving. So I just wanted to point that out. Now, Newton's first law. It's usually quite long in writing it, but I'm going to give you the short version of it, and just that object. Let's see here. Object at rest stays at rest. That's the main thing here. And the same thing with an object in motion. Okay, so an object in motion also wants to stay in motion.
ناوي تروح على ايه؟ ابغى تعمل شيفت يا زلمه.
So this means if I'm still, I'm going to want to keep being still, so to speak, unless something sort of kicks me and moves me. Same thing, if let's say you're in outer space and you're in a spaceship and flying in a straight line, you're going to want to keep going in a straight line unless something else causes you to move. So that's why I'm going to say unless
بدي شلون أتني disconnect.
ما عرفت ليش قتلك مو بأول ثانية. مو فورا قتلك. Here's the key part here. Unbalanced force. رقعته أنا إنه playing ما بعرف شو كان اسمه. I'm just going to change my little A here because it was ugly looking. Oops, I didn't really make it better. So unless you're acted on by an external unbalanced force.
Orange, Verbal, can you buy me something, please?
So the key thing here is that F
M4 maybe.
Net
Blue.
Is not zero, this unbalanced force. So what this means is that you're going to want to go in a straight line unless something comes and is an unbalanced force, right, which means the net force is not zero. It's not a situation like this. It could be a situation where, like, I don't know, well, let's do an example. Let's say you're a cyclist.
We have the bomb.
I live in Denmark and everybody here seems to be on a bike all the time. So let's say I have a cyclist. So my cyclist, let's say I'm biking along and there's a little piece of wall here. So maybe this is my bike here. I gotta try to draw a bike nicely. Let's see, bikes go like this sort of. So then here's me on my bike.
Where?
I guess there's a seat here and there's my legs. And I'm biking along and I'm moving this way. Okay, so there's my speed here. I'm moving that way and there's this wall here. Well, what happens, of course, is that this is before. Now after, of course, is not going to be very fun. Afterwards, I just have a mess, a jumble of bike here, and I just go flying. Okay, so I can actually go flying. And the reason why I go that way is because of Newton's first law. It's because I am moving, my bike stops suddenly, but I want to keep moving. See, I tend to stay in motion. So as a result, I go flying, and that's maybe why I get hurt. Another example is seat belts. That's actually why you want to wear your seat belt. Because if you don't wear a seatbelt, you're in your car runs into a wall, but you and the car are separate objects if you're not strapped in to your car. Which means is, as you drive, if the car stops, it's going to be like being on a bike here. The car is going to stop suddenly, but you, if you're a free object not strapped in, you're going to keep flying. That's why you can get hurt by putting your face in, I don't know, the steering column, or some people have even been thrown completely out of a car. And that's because of Newton's first law. It also comes into effect with circular things. So for example, what if I have some sort of rope on the end of a string, a weight on the end of a string, and I would, swing that above my head like this. As I'm swinging it, if we looked at a top view of that, You know, so let's say I'm swinging it around. As I swing it around, you know, it's going around like this, right? This is sort of the direction. But the question is, what if I let go of the rope? Which way will it keep going? That's actually a common question I like to ask students just to see, because a lot of people think it's going to keep moving in a circle, but it doesn't. And that's the whole reason why, you know, one of these sort of slingshots, you know, if you actually move something around and then you threw it, it goes in a straight line. The only reason it wasn't going in a straight line is because there was a string there or something else there that was unbalanced, that was causing it to go around in a circle. So when that force stops, let's say I cut the string or let it go, it tends to go in a straight line. Okay, so if I let it go, it would actually, oh, that was a horrible sound. It would actually keep going in a straight line. So that's really important. So I think Newton's first law is especially important in our own everyday lives, because we experience these things a lot. I mean, if I am at rest, my body doesn't tend to want to move unless, you know, something pushes it. It's actually related to inertia, but that's not something that we need to talk about in physics SL. But it turns out inertia has to do with this. It has to do with, you know, why it may be harder to push a train. So for significant figures, it's related very much. Yeah, just these. So for significant figures, it's related very much to uncertainty. And I love this this drawing, this picture here of Keanu Reeves. You know, you're supposed to round something to 4 sig figs. What do we mean by this? I think a lot of people spend too much time worrying about, you know, how many significant figures to use. A good rule of thumb is to actually use the least good one. So what I mean by that is, if you've been given a whole bunch of different values, so this has to do with making measurements. So let's just say, or, you know, using values on, you know, on exams. So let's just say you have different choices. You have like 2.0 is one of the values you're given, and maybe like 17.458.
I go toilet.
And maybe you're given like...
Good luck, first round.
Yeah, just these two, for example. Let's just say these are the two numbers you used in an equation in order to actually solve something. Then what you would do is, when you're finished with your answer, if you got an answer that had a whole bunch of different digits, like this one right here, like this 17.458, you would actually use only 2 right here. So you'd only use these 2 right here. You'd have something, point something else. That's the main thing really to worry about as far as significant figures go. Just use the least good one. I think that's sort of a good rule of thumb here. So what do I mean by significant figures and uncertainty? When you're actually making a physical measurement, so let's just say you measure like the length of my, I don't know, this right here, whatever this is. Let's just say it's the length of, I don't know, an eraser or something like that. When you make a physical measurement, that means that you're going to, you measure it with something, some device, and that means there's going to be some uncertainty on the actual measurement. In other words, you don't know it exactly. You might say it's like 5.8 centimeters, but it's not exactly. It's plus or minus a little bit. So this plus or minus implies the sort of shaky nature of measurement. So for example, I just want to focus on one thing, especially for physics here, is usually the uncertainty is just one non-zero number. So what do I mean by that? I mean that, you know, later on when I show you, you know, in videos how to actually calculate uncertainties, you might end up calculating something with a whole bunch of digits. So for example, let's say you get something that says like plus or minus 0.052 like I have here. This implies that you're so certain about your uncertainty.
Who the fuck shot me from you, is stupid.
Which is a little bit weird and counterintuitive. So what I'd like to tell you is, for this one here, what I would probably do is think about this and say, okay, you just need one non-zero number. So in this case here, I would just need the 0.05. So that would mean I would have to actually round this right here. My uncertainty itself, I need to make it, I'm only allowed one non-zero number. I'm allowed zeros to the left, I'm allowed zeros to the right, but usually that's how we write uncertainty. So in this case right here, I would write 0.05, and I would think about rounding. Do I have to round that number up or down? In this case, I don't. So do you see, the first thing I always check for is does the student have one non-zero number? So in this case right here, yep, good. So that's a properly written uncertainty. Let's say you did another calculation and you got this like plus or minus 15.29. What do you do there? You're only allowed one non-zero number. So what I would say is you'll probably have to round on this to tens digits, so to speak. And that means I would either make it 10 or maybe 20. And it depends how you like to do your conventions here, but most people will say that a 5 afterwards will make it round up. So in this case right here, you'd end up with plus or minus 20, whatever these units are. And the reason I know this is okay is because, see, I've only got one non-zero number. What I like to tell students, we go more detail like this. I say, make a non-zero number sandwich. So if there's a whole bunch of, things in between like this right here, you would do this. That would be sort of for the significant figures. But I wouldn't worry too much about it. The key thing as far as your exams go is knowing how it is to actually write these uncertainties. So first of all, make your uncertainty a non-zero number. Next, once you know the uncertainty is a non-zero number, it's the uncertainty that drives how many significant figures you should use, not the other way around. So I'll give you a few examples. So let's just say here, I just wrote out a couple here. So let's just say we have, let's say you did a measurement and you actually measured through some device or something like that, some length, let's just say, is 2.128427 meters. You measured it somehow super accurately according to your little device that you used. But your uncertainty is 0.001 meters, let's just say. So first of all, you need to check, I want to write down this value. And let's just say I want to write down the length. All right, the length is going to be, this number, this 2 point whatever. Don't just say this plus or minus 0.001 and say you're done. Because you see, there's a problem now with how many significant figures you're allowed to use. Or in this case, I like to think of it as how many digits you can use, how many numbers you can use to represent this. You're always allowed to use you're always allowed to use scientific notation. So what I would do here, for example, is look, okay, first of all, is my uncertainty one non-zero number? Yes, it is. Now, do you notice that it's the third digit after the decimal? See that? After the decimal, it's 1, 2, 3. So that means, remember I showed you before here, it's the uncertainty that tells you how many significant figures to use. So in this case right here, I'm allowed 3 after the decimal, so I have to round here. So what that means is I can say my value is L equals 2.128. I have to stop there. I would round up or down. In this case, I just leave it. Plus or minus 0.001.
No. I have a friend of mine have the best hacks ever.
This actually could be my answer. This could be my final answer. I could say, all right, that's it. Because
homemade,
just homemade. If someone did it right, you first check, is it one non-zero number? Yes. Are you rounding on the same digits? In other words, 3 after the decimal, 3 after the decimal? Then you got it. Let's look at the other one here. Let's say you make a measurement of force, and somehow you measure it or you calculate it. When you're actually using your calculator, you actually type it all in. And you end up with a number of 259.4. Right, because that's a measured thing. But your uncertainty is supposed to be plus or minus 10. So what do you do? This is for newtons. Again, you don't just say plus or minus 10 right here, right? You don't actually say just that, right? You can't just say that. You have to write it properly. So what I would do is I would say F equals, and think about this, 10, that's rounding in the sort of tens digit. So that means I have to round here, because this is 259. So that means I would have to round here. So I write my 2. And my 5, however, though, will round up. Do you see that? Because the 9 makes it actually round up. So that means it becomes that 6. And I'm only allowed a 2 and a 6. I can't use any other numbers to represent it. The rest of it just has to become zeros. In this case here, it's just going to be 0. Now, I don't say 0.000, something like that. I'm not allowed that many digits. So I just say 260 plus or minus 10 newtons. So this right here could be my answer. So I hope this explains it. It's a really, really simple concept, but a lot of people mess it up. And just so you know, this shows up, this is immensely important for paper 3. Because the first part of paper 3, you have to do a lot of this sort of calculations, and it really helps to be able to understand how to actually represent your answer.
Orange bomb.
These definitions of accuracy, precision, and error become really important, especially on paper 3. In the first part of paper 3 especially. In the first part, it's called section A, where you've got all these questions about the prescribed experiments. So in this, those definitions, especially about error, become really important. And I like this Star Wars reference here about, only the Imperial Stormtroopers are so precise. And these definitions themselves aren't actually that difficult, but you need to know them really well in order to actually succeed in your exams. So let's look at the word accurate. The word accurate, what we mean is a small systematic error. And I'm going to explain the word systematic error as well. But it means they're close to the real value, the quote-unquote real value. So what do I mean by that? Let me see if I can do, just paste something. Yeah, good. So let's just say you're doing, I mean, this is the old trope. Everybody uses archery as an example, but it actually works. So let's just say I'm doing a whole bunch of archery here. And I want to see something that's accurate. So a small systematic error. That means they're close to the real value. So in this case right here, let's see something then that is, let's see, I'll try to draw on it here. So let me say something right here that is, let's just say like this here. So really close to the real value. So this one right here, for example, if I shot a whole bunch of arrows right here, do you notice they're close to the real value? In other words, in this case, they're close to the center or whatever they're supposed to be. So they're pretty close to this right here. So we could say these are accurate. Now I'm just going to show you the contrast. Just so we can actually we've got the word after that called precise. And there what it means, there's a small random error. And what I mean by that, they're close to each other. So what I'm going to try to do again is paste something here. Yeah, there we go. Do another one. So I'll show you something else then that's small random error. Do you know, by the way, I'm going to define them a little bit clearer too. I'm just going to start with this. So let's do something then as a small random error. Let's say I shot a whole bunch of them, but they're all really close to each other. Maybe they're all right here. Whole bunch of them. They all hit right over here. This case right here, you can see these are here are precise. Now these words accurate and precise, something can be accurate and precise, it can be accurate and not precise, and so on. So now take a look at this. So again, precise means close to each other. They're grouped close together. They don't necessarily have to be where they need to be. So in this case, these are precise, but you could say they're not accurate. Do you know how you can say that? Because if they are accurate, they'd also be close to the center. In this case here, they're accurate because they're close to the center. And it depends on if you want to consider this close to each other or not. Then, you know, it's a bit of a dodgy definition. In this case right here, you could say, but not precise, you know, because you could say that, well, they're not totally close to each other. Again, it just depends what you mean by close, doesn't it? So maybe we'll go into these definitions a little bit more detail. So systematic error. What do we mean by a systematic error? It means that everything is off by a certain amount. So in this example back here, you know, I said there's a small systematic error. In other words, things weren't off by very much. Whereas over here, can you see you're trying to shoot the center of the target, but instead you're way off all the time. So in this case right here, everything is off by a certain amount. And what I mean by that is that, more experiments, they won't help. You probably need to recalibrate. And an example of that could be, let's see here if I can get a little pen going here. So let's just say you're doing an example of something like Hooke's Law. That one where you have a whole bunch of data points. So let's just say I have some things here. I'll draw some error bars here. So I have one here. What do you want? Here. Let's just say. So I'm just drawing myself some data points with some error bars, like this right here. And if I draw a line that best fit through this bad boy, let's see here what I would get. See if I can draw that. That would be something like this, right? Not exactly, but something like that.
Behind us, holy fuck.
So if you take a look at this, you can say, all right, so there's my point, there's my uncertainty, so my error bars on those points. But if you know about Hooke's Law, at 0, this would be like a spring. You know, if you've got a spring and you attach some weights to it, some masses to it, as the spring extends, you know, that'll be the force on it. So the force on it as it increases, the extension will increase. So in this case, that's what this would be a graph of. And it would make sense that at 0 displacement, it should be for 0 force. So in other words, this thing, you're expecting it to pass through 0, 0, but it's not. So in this case right here, can you see that? Right here? Whoa, I didn't mean to do that. Don't mess it up there, Mitch. There we go, like this. This one right here, do you see we're off by that same amount? We're always off. So we're off by this amount. So this means we have a systematic error. In other words, every value you did is off. It's sort of messed up by the same amount. So if you just repeated it a lot, it wouldn't change. You'd still just be off by the same amount. You need to recalibrate. You need to maybe remeasure things in order to fix it. By contrast, a random error, this is where the data points don't match the others. So maybe I'll do an example of that here. So I'll just show you some data points here. So let's just say I'm drawing some data points. So here's a data point. Let's just say And here's another data point here. I'm just drawing some data points with some error bars here. And then I have a point that's over here. Let's just say something like this. I'm drawing it poorly, of course. But you see that, I mean, if I drew a whole bunch of data points like this here, you'd see that, you know, most of them match, and most of them seem to follow this dotted line, or this line, right? Most of them seem to match. But there's this one weirdo point. There's one that just doesn't really fit. That is a random error. That one right there is the one that's messing everything up. You probably made a mistake. Probably. Or just something weird. In this case, more experiments will help. You see that? Because if you do this, more experiments are going to help because you're going to reduce your random errors. So for systematic errors, more experiments don't help. You need to recalibrate. But if you have random errors, more experiments will actually help. I'm going to have an example. Oh no, wait, not an example. Really important, actually. Yeah, I'm really glad I checked this. Line of best fit. Oh my god, this is so important. Does it need to be a straight line? In other words, if you're looking at something like, you know, you got some sort of graph. It doesn't matter what it's a graph of, right? It could be, I don't know, potential difference versus the current. Let's just say. And you expect to do a straight line, maybe, I don't know. Maybe you get data points that do, you know, something like this right here. And maybe then, oh, I don't know, maybe it does something different. Maybe it's something like this. So the question is, does it have to be a straight line? And maybe I have another point maybe up here like this. Well, not quite like this, but maybe way up here like this. There we go. So the question is, does it have to be a straight line? No. So that's the answer for sure. It's no. It just has to fit through the error bars. That's the key thing. In other words, if I was trying to draw a straight line through this right here to make it pass through all the error bars, I probably can't. At the bottom right down here, all the way up to the top right here, I probably can't make it pass through all the error bars. So if that's the case, you can actually state it's not a linear fit. You know, this right here, for example, is something that's going to be a curve. That might be my line of best fit. The lines of best fit do not have to be straight. They just have to pass. This is the key thing. They need to pass through the error bars. That is the key stipulation here. This is what has to happen. They gotta pass through the error bars. As long as they do, it can be whatever curve you need. Now I have an example. So let's just say we're given an archery target and you're given this right here. And you might say, do you have, because before I define these as accurate versus precise, let's see, this was, for example, a question very, very recently on an exam on a paper 1. This for SL and HL, and the question had been asking, you know, what kind of uncertainties do you have? So try to think about it. Do you have random uncertainties? Do you have systematic? Do you have neither? Or do you have both? Think carefully about them now. So instead of accurate and precise, you got to think about them as random versus systematic. First of all, I can say, so here's the answer. The answer is, let's see. First of all, we have systematic errors. Do you know why we have those? That's because they're off from the center. Do you notice? Like they're not at the center. They're off a little bit, aren't they? So we have systematic. How about random? Do we have random errors here?
Sorry, my mistake. Fuck.
I would say yes, we have random errors because they're also not so close to each other. Do you notice they're a little bit spread out? Had they been all tightly grouped, then you could say there's very little random errors. So in this case, I would say, yeah, you have plenty of systematic errors and you have plenty of random errors as well.
I'm going to bathroom, my friend. Good luck.
Uniformly accelerated motion is one of the most basic things that you need to know from physics. And I don't mean basic as in easy. I mean basic as in base. As in a lot of things really hinge upon this, especially an understanding of it. So I'd like to maybe go a little bit by contrast and talk about what happens when you're not accelerating. So see, if you're actually not accelerating, then it becomes really, really easy. Okay, if you're not accelerating, you have nice, easy equations of motion. In this case right here, your speed or your velocity will just be equal to your distance or displacement divided by t here. So it'll be s over t. Some people call it distance over time. That's also fine. Right, so something like this in seconds, and this is in meters. In this case right here, super, super easy. Okay, if not accelerating, really, really easy. I love this picture here, accelerate to attack speed. So There are 4 equations of motion. You really need to know these ones are here. You don't have to know them by heart because they're on your data booklet, but you do need to know how to use them. There's one extra one that's really important, I think, as well, so I'm going to actually put it down here. It's sort of a general definition of acceleration. If you're accelerating, it's your change in velocity versus time. Technically, it's a vector, so I'm going to be really careful here and actually go like this. So this right here is the acceleration is technically the change in velocity over change in time. That is sort of a key thing in physics. So maybe we'll talk about this. If you're accelerating, remember it means your speed is actually changing with time. What that means, imagine if you're driving in your car. If you're going at a constant velocity, if your velocity is constant, then you're not accelerating. Right? That's maybe we should say v equals constant. So if your velocity is constant, you're not accelerating. So what that means, then you could still be in motion. Right? Because you're not accelerating doesn't mean you have to be stopped. You could still be moving. Right? You could be in your car going at 100 kilometers an hour. So if you're driving at a constant 100 kilometers an hour, think about your speedometer. Or if you have digital one, then... But the numbers will actually just remain the same. You'll be just at 100. You're not changing. Therefore, you're not accelerating. If you are accelerating, that means your velocity is changing. Do you see it came from that literal definition here? That acceleration is a change in velocity. So anytime your speed or velocity is changing, you've got some sort of acceleration here. Now there are these 4 main equations of motion which you don't have to memorize, but they go v equals u plus at. You've got s equals ut plus half at squared. You've got v squared is u squared plus 2as. You got the other one here with s equals v plus u times t over 2. It's important to make sure you know what all these different letters mean. So that's why I'm going to add to them here. So remember that s is your displacement. I always thought that was strange that they call it displacement. You'd think it should be called d, right? But S is displacement. It just seems silly, I think, to an IB student at least. Like, what is it? Displacement? But I mean, if you think about if you're doing calculus with all stuff, like with derivatives, we use the symbols d, and things like that, then it gets really confusing. So that's why, okay, displacement is fine with an S. Initial velocity. Or initial speed. We'll use these as the vector ones actually, so this will be good. So So should this scalars. See, time is a scalar, so you don't have to worry about it. But this is technically how it should go. So if we do this, the initial velocity is going to be measured in, you know what velocity is? It's a rate of change of position. So in this case, remember velocity is change in displacement over time. That's how you can define velocity. And if you define it that way, then you can say, look at the units of this thing. Look, it's like a slope, isn't it? In fact, if you have a graph of displacement versus time, right? Displacement is in meters, time is in seconds. You have a graph of displacement versus time with like this. The velocity is just going to be, let's see, delta s, delta t. That's the slope of the tangent.
F1 guys.
So what that tells you then, for example, right up here, can you see the tangent line?
F1, you fuckers.
It tells you then that the speed right here, or the velocity right here, is going to be 0 because the slope.
Well, you are hacking, you fucker. You are hacking. Hacker, sucker.
So let's go into this units then. If the velocity is dependent on the displacement, units of displacement are meters, units of time are seconds, so that's why it says meters per second. I'm just trying to show you where everything came from. Like I said, it's a basic because it's a base. Final velocity, same thing. Because remember, if you're going to accelerate, you're changing your velocity. So what does it start off at and what does it finish at? That's u and v. Acceleration is literally this thing right here you're talking about here. It's this change in v versus t. And again, look at the units. Doesn't v have units of meters per second? Right, we just talked about it right here. Right? V has units of meters per second, and you're dividing by seconds. So it's meters per second. That's why it's meters per second squared. That's why I write it like that, meters per second squared. Time, of course, is in seconds. We're going to say s, but I like to put seconds. So these are these main equations that you need. These are the different letters, different variables you're going to be using. Now, there's a nice little trick here for solving lots of acceleration equations. I like to call it UVAT. Some people call it SUVAT. It doesn't matter. But basically, you should use this sort of trick here. At least I think it's a good way to do it. If you're not super good at this, it's a good trick. What I like to do is, this basically tells you your shopping list. So what I would do is I would, split up. I would actually write down, what do I know? Do I know what U is? Do I know V? Do I know A, S, and T? If I don't know something, I put a question mark. If it's the thing I want, I put a star. I'm really careful with pluses and minuses if it goes up or down or whatever. And I always make sure that the only things that go in here are in proper units. In other words, if they're being sneaky and they gave you something in centimeters, let's just say, make sure you convert that to meters. So in my own rules, at least, that's how I deal with this. Maybe let's actually do an example. So here you're driving in your car. Oh, by the way, I like this. Decelerate, because you're going to be talking about decelerating. I like this. Decelerate to regurgitate the celery you just ate. So you're driving in your car and you're going 21 meters per second. It's just the notation is a bit weird, but basically your initial speed, remember, initially you're going this. So that means U now is 21 meters per second. You slam on the brakes. What that means is you slow down, don't you? You decelerate at 3.2 meters per second squared. So acceleration is 3.2 meters per second squared. But you got to watch out here. If you're decelerating, let's just assume you're going to the right. Let's just maybe assume. We'll draw our little situation here. So here's your car. I'm a really lousy artist, as you can see. So your car is initially going with some speed 21 meters per second. And what happens, of course, at some point, you're going to be stopped, won't you? So at some point, oh god, my drawing got even worse. My speed is 0. So to do this, think about this. What's the direction of my acceleration? My acceleration has to have an opposite sign to the speed. Because you see, if the speed is going to the right, then you need to define your acceleration as to the left. So I'm going to put a negative in front of it. No, the acceleration, otherwise, the acceleration would be positive 3.2. That means you'd be starting at 21 meters per second. And you'd accelerate, like, you'd actually, put on the gas. And you'd end up going way faster. And that's not the situation here. So somehow you have to account for it. I like to just make my initial speeds in the positive direction. And anything that's opposite of that, I just throw a negative in front. So how long does it take for you to start? How long? That implies a time. This is what we're looking for here. So what I'd like to do then is just show you that whole UVAS thing or SUVAT or whatever you like to do.
Nice game, baby. Keep studying.
I just put in what I know and what I don't know. This helps me to pick which equation I should use. So U, the initial speed is easy. It's 21. It's meters per second.